Yes, ladies and gentlemen, welcome to today's lesson. This is lesson 3. We are continuing from where we had left on soil physics, and this is soil physics part 2. Today we are going to be discussing quite a lot, and under subheading soil consistency, soil particle density, soil bulk density, soil porosity, soil color, soil permeability, soil temperature, and soil hydraulic conductivity. I'm Sylvester Odundo, a trainer at Friends College Kaimosi. My email address is odundosylvester54 at gmail.com, and my number is 0706 248 870. We want to talk about consistency. What is consistency? Now, soil consistency is the resistance of a soil to deformation or rupture, and is determined by the cohesive and adhesive properties of the soil mass. And knowledge of this consistency is very, very important, especially in tillage operations, in traffic, and in pond construction. Consistency gives an indication of the soil texture. Now, when we are talking about soil consistency, we are talking about soil being described as wet soil, and examples of wet soils we may have ranges between non-sticky to very plastic. Then we have moist soil ranging between loose and extremely firm soil. And lastly, we have dry soil, which we may have examples of very loose and extremely hard soil. Now, these diagrams gives you an indication of what soil consistency is all about. You just take your soil, you add a little bit of water, you rub it on your palms. If it can be able to stretch for as long as 0.3 millimeter, then you can refer that soil as sticky. While if it cannot be able to hold together, then that means that that particular soil is non-sticky. We want to also talk about, ladies and gentlemen, I want us to talk now about density, and we'll be actually talking about soil particle density and bulk density. Now, what is soil particle density? When we're talking about soil particle density, then it's very important for we to know that actually it is the mass per unit volume of soil particles, the solid phase. When we are talking about the solid phase, we mean the part that only is the solid. Remember, soil has it is made up of gases, liquid, and solid. So it is the solid, the volume of the solid particle, the mass per unit volume of soil particle, expressed in grams per centimeter cube. Presence of organic matter decreases the density. Why? Because organic matter is less dense compared to iron compounds in a particular soil. And when organic matter is a constituent of a particular soil, then that means the mass of that particular soil is going to be less compared to the other soil that has iron compounds in it. And that's why presence of organic matter, therefore, decreases the soil particle density of a particular soil. Particle density represents the average density of all mineral composed in the soil. It is very important for you to know, because we have said we get the unit mass per unit volume of the solid phase. Most soils, therefore, will have soil particle density value of 2.65 grams per centimeter, because quartz, which is the dominant mineral in the soil, has a density of 2.65 grams per centimeter cube. Particle density, remember, varies little between minerals and has little practical significance, except when we will be calculating the pore space. And we are going to see how this particle density comes in when we are calculating the pore spaces. And important for you to note is that particle density has a formula, and this formula is you getting the oven dry soil of a particular soil divided by the volume of the soil solids. And we can also say that particle density can be determined. You can be able to determine this parameter using specific gravity bottle technique. Now, let us talk about now the bulk density. Is also very closely related to particle density, but I want you to notice the difference. It is the mass of soil per unit volume of soil. Now remember, on the other side we are talking about the solid phase, but here we are talking about volume including both soil and pores, expressed in grams per cc. A sample must be taken without compaction or crumbling to correctly determine the particle density. Remember, that is very important. You should not compact that soil because you're going to affect the pores in it. You're going to affect this the volume as a result of any compaction. So you need to take care of that. Then it increases with depth and tends to be high in sands and compacted pan horizons, and tend to be low in soils with abundant organic matter. Again, organic matter, we are seeing here that it influences the soil bulk density by reducing. If there's a lot of organic matter, then you end up having soil bulk density which is low compared to a soil that doesn't have organic matter in it. Well, now tillage operations loosen soils and temporarily lower bulk density, while compaction processes raises bulk density. Remember, when we are carrying out plowing or any tillage operations, then that means we are opening the soils to air so that it can be able to move in easily. And as a result of that, because we say that it is actually the mass over the volume that includes both soil and pores, then you find that because of the air spaces as resulting from loosening of the soil, then you find that bulk density is lower compared to a soil that is compacted. So high bulk density corresponds to low porosity, and natural soil forming processes that increases aggregation reduce bulk density, but excessive tillage and raindrop impact on bare soil destroy aggregation and increases bulk density. So what's the formula? The formula is bulk density is equal to oven dry soil weight divided by volume of soil, solids, plus volume of pores. And lastly, we can say that you can be able to determine bulk density by taking soil core samples of non-volume in the field and determining the oven dry weight. Next, we want to talk about soil porosity, and the next bit is very important, and we are talking about soil porosity, and we are saying that soil porosity is that portion of the soil volume occupied by pore spaces. It is normally calculated using values determined for bulk density and particle density. So before you get soil porosity, it is important for you to have first calculated the bulk density and the particle density. So the formula for soil density, for soil porosity, therefore, is percent solid space is equal to bulk density divided by particle density. For you first need to get this on this solid phase, because when a soil is not waterlogged, then you expect that that particular soil will have air and the mineral part, which is solid. So to get the solid phase, or the solid space, is equal to bulk density divided by particle density times 100. And therefore, to get the porosity, then it is very easy. You just get the difference of the solid space from a total of 100. And the diagram that we are seeing there gives us some kind of an elaboration of the nature, or the how the soil looks like when compacted and when under normal condition. So you are seeing here the blue color shows water filtration is very fast because the air spaces are very many. Then you find that in this other one, the air is also the air movement or circulation is also enhanced when a soil is not compacted. But on this other side, you find that the movement of water and air is impaired or obstructed. Next, we want to give you, now we have a sample calculation of soil porosity, and the question goes, a 260 centimeter cube cylindrical container was used to collect and disturb soil sample. The container and soil weighs 413 grams when dry. When empty, the container weighs 5 grams. What is the bulk density and porosity of the soil? First, we need to remember that we have been given the weight of the container to be 75 grams, and the weight of the container plus soil is 413. So if we are calculating the bulk density, therefore we need to get the difference of the container plus soil, subtract the weight of the container, so that we have 413, which is the weight of the soil and the container, subtract 75, which is the weight of the container, then we have 338 grams of soil. Now, if we want to calculate the bulk density, therefore, it will be the mass over volume, the mass of undisturbed soil over the volume of the soil, and that gives 1.3 grams per centimeter cube. In calculating to determine the soil porosity, therefore, we have been given the bulk density to be 1.3 grams per centimeter cube, and the particle density in most of the soils, remember when we mentioned about quartz being the dominant mineral matter in a soil, then it gives us 2.65 grams per centimeter cube. So the porosity therefore is equal to 100, subtract the value that you get of bulk density divided by 2.65 times 100, and the answer is 51%. So the next topic or parameter is soil color, and it gives an indication of the various processes going on in the soil as well as the type of the minerals in the soil. Now we are talking in terms of hue, value, and chroma. Actually, that is how it is described. Now, when we're talking about hue, it represents the dominant wavelength or color of the light. Value refers to the lightness of the color, and chroma, relative purity or strength of the color. Now, the soil color is normally determined by a comparison of the sample with a standard set of color chips mounted in a notebook called Mansell Soil Color Charts. Very important for you to note is also that soil color is normally identified using the Mansell color charts, and the right hand top corner represents the hue, the vertical axis the value, and the horizontal axis the chroma. Let's continue with soil color, and what we are saying, in addition to what we have just mentioned, is that it depends on the mineral composition of the parent rock and the organic matter, such that if a soil contains a lot of iron, then you expect that soil to be brownish, yellowish, or reddish in color. If it is white in color, you expect silica to be dominant in that particular soil. Soil with a lot of humus is gray or darkish in color. For example, the red color in the soil is due to the abundance of iron oxide under oxidized conditions, a soil that is well drained. And dark color is generally due to the accumulation of high decayed organic matter. Yellow color is due to hydrated iron oxides and hydroxides. Black nodules are due to manganese oxides. Mottling and glazing are associated with poor drainage and or high water table. And abundant pale yellow mottles coupled with very low pH are indicative of possible acid sulfate soils. Colors of soil matrix and mottles are indicative of the water and drainage conditions in the soil, and hence suitability of the soil for aquaculture. Soil permeability is the other parameter, and it can be defined as the ability of the soil to transmit water and air. As the soil layers or horizons vary in their characteristic, then you expect that the permeability will also be different from one layer to the other. And we can authoritatively say that pore size, texture, structure, and the presence of impervious layers such as clay pans determines the permeability of soil. When we are talking about clay pans, we are talking about the hard pans that may end up forming in the subsoil that will prevent water seepage in that particular soil. Permeability, therefore, is measured in terms of permeability rate or coefficient of permeability. Now, that particular picture that you're seeing is a hand showing a column of soil, and there is a continuous flow of water, and down there you can be able to calculate to see how much water is able to seep at a given time. So that is what actually we refer. Now, on soil permeability determination, we are talking about rate or coefficient of permeability being determined in the laboratory by measuring the rate of flow of water from a constant head of water through a column of soil at a specific moisture content and other conditions. Remember the picture that I showed you in the previous slide showing a hand with flow of water through a column of soil? That is actually what is used for purposes of determining the soil permeability in the lab. when we are in the field, we also have a way in which you can be able to determine the soil permeability in the field, and this can be achieved by first making a hole approximately 30 centimeter diameter, smearing the sides of the hole with heavy wet clay or lining with a plastic sheet, and measuring the rate of infiltration of water by filling the hole repeatedly with water and noting the time it takes for the water level to go down by a specific depth. Now, a soil that is suitable for aquaculture or for making the bottom of a pond should not be greater than 5 times 10 raised to power 6 meters per second as its coefficient of permeability. This is according to Koch and Longley 1985, who has done quite a lot, did quite a lot of studies in the area of determining the soil permeability of different soils of that particular the soil permeability of that particular soil. Soil temperature is another parameter, and it depends on the ratio of the energy absorbed to that which is lost. And when we're talking about soil temperature, we're talking about the rays that end up reaching the Earth's surface, and some of it is reflected in form of infrared, and that little which is absorbed actually changes or influences the soil temperature. Soil has a temperature range between negative 20 to 60 degrees Celsius with a mean annual temperature from 10 to 26 degrees Celsius. Soil temperature regulates quite a number of agronomic practices such as seed germination. You expect that if the temperature is high, then the seed germination is going to be a little bit high compared to a soil with low temperature, and therefore you expect the seed germination to be a little bit slower or very poor. It also helps in breaking seed dormancy, such as it influences seed dormancy in such a way that if the temperature is a little bit high, then you expect the seed to actually break its dormancy, and vice versa is also true. Another agronomic practice that may end up being affected by temperature is plant and root growth and its development. You expect that the temperature will end up enhancing the development of the roots of a particular soil compared if that temperature was a little bit low. The availability of nutrients will be made available faster in a soil with high temperatures compared to a soil with low temperature, because temperature acts like a catalyst in that particular soil. So therefore, soil temperature has important seasonal, monthly, daily variations, fluctuations in soil temperature, therefore being much lower with increasing soil depth. Heavy mulching, which is a type of a soil cover, can slow the warming of soil in summer and at the same time reduce fluctuation in surface temperature, while clear plastic mulch will end up raising the soil temperature because the clear plastic allows the rays of sun to penetrate and hit the Earth's surface. Still on soil temperature, more often agricultural activity must adapt to temperatures by maximizing germination and growth by timing of planting. This, we can also say, it is determined by the photoperiod, that is the hours of sunlight during a day. Next, we also are saying that if you optimize the use of anhydrous ammonia by applying to soils below 10 degrees Celsius, then you can also be able to adapt to soil temperatures that are very low. And if you can be able to prevent heaving and thawing due to frost from damaging shallow root crops, then you also be adapting to agricultural activities unhindered by the soil temperatures. And also preventing damage to desirable soil structures by freezing of saturated soils. And lastly, by improving uptake of phosphorus by plants. If you can be able to increase the temperatures of the soil by using, for instance, dark mulch, then you expect at the end of the day that the uptake of phosphorus is going to be enhanced. So we can summarily say that soil temperatures can be raised by drying soils or the use of clear plastic mulches, and organic mulches therefore will end up slowing at the end of the day the warming of the soil. Ladies and gentlemen, what are the factors affecting soil temperatures? One, we have soil color. A soil that is bright in color, you expect it to have low soil temperature because most of the soil is reflected, compared to a soil which is dark in color, which ends up absorbing the heat from the sun. Then we also want to talk about The relief, when we're talking about relief, you need to remember that we are just talking about the slope of a particular soil orientation and elevation. If a soil is in high elevated places, then you expect that soil temperature is going to be a little bit low compared to a soil with in a lower elevation. Then a soil cover, you expect that shading and insulation will end up causing that particular soil under insulation to be a little bit lower in terms of its temperature compared to a other soil which is not shaded or insulated. Air temperature of a particular place also determine or affect the soil temperature in the sense that if a particular soil is in an area with very high temperatures, you expect that the soil is also going to be highly in terms of the temperature compared to a particular in another soil where the air temperature is low and therefore the soil will also be low. The color of ground cover and its insulating properties therefore have a strong influence on the same temperature, and we can also say that whiter soil tends to have a higher albedo than blacker soil cover, which encourages white soils to have low temperatures. Next slide, we want to talk about the soil hydraulic conductivity, and we are saying that it's a quantitative measure of saturated soil's ability to transmit water when subjected to a hydraulic gradient. It can be thought of as the ease with which pores of a saturated soil permit water movement. And also, according to Darcy's law, saturated hydraulic conductivity is a constant or proportionality constant that defines the linear relationship between the two variables, J and I. Now, J is hydraulic gradient and I is the influx of water. Now, just on the same, it is the slope of the line, that is J divided by I, showing the relationship between the flux and the hydraulic gradient. Hydraulic conductivity is a slope, therefore, that defines the proportionality relationship between flux and hydraulic gradient, or in this case, an unidirectional flow in saturated soils. So how do we determine hydraulic conductivity? Remember that you need to have flux that represent the quantity of water moving in the direction of and a rate proportional to the hydraulic conductivity. If the same hydraulic gradient is applied to two soils, the soils from which the greater quantity of water is discharged is therefore more conductive compared to another soil which has no or less quantity of water that has been discharged. Okay, good. So next, we also want to say that therefore sandy soil will yield a higher flux or is more conductive than the clay soil at the same hydraulic gradient. The soil with a steeper slope therefore also has the higher hydraulic conductivity than a gentler place where that soil compared to another soil in a gentler slope. Solving Darcy's law for hydraulic conductivity therefore is J, which represents the hydraulic gradient divided by the influx of water. Now, Darcy's law, that is gives a kind of a diagram just to explain the relationship for the flow of water through porous medium known as Darcy's law, which states that K, which is the flow rate, is equal to a constant with the coefficient of permeability, I, which is a hydraulic gradient, and A, which is the cross-sectional area of a particular column through which the flow happens to occur. Ladies and gentlemen, we have come to a close today, and it's always a pleasure to have you during our learning session online. It is a big thank you, and remember to keep on subscribing, share with your friends, and bye for now. See you next time.